In this video, we will talk about how to determine if a vector is a linear combination of other vectors. So suppose we have the vector u1 and the vector u2 and the vector v, and we want to know, is v a linear combination of the vectors u1 and u2? Or another way to write that is, could we write some formula like c1 times u1 plus c2 times u2 is equal to v, where c1 and c2 are just some constants? Is it possible to write this formula? Well, the way that we can figure this out is that we can put all three of these vectors into one augmented matrix, and then we can use elementary row operations to convert the matrix to reduced row echelon form, and then just see if that reduced row echelon form matrix has at least one solution. So let's go ahead and do that. So we'll say the first column of our matrix is just going to be the values from vector u1. So 3, 1, and negative 1. The second column will be the values from vector u2. So we'll write 2, negative 2, 1. And the augmented column will be the values in vector v. So 4, 4, negative 3. So we've written our augmented matrix. Now we want to transform this matrix into reduced row echelon form. And I'll link to another video that I have on reduced row echelon form, just as a quick reminder of what that is. So to start with, it helps if our first pivot entry in the first column right here, or in other words, the first non-zero value is a 1. So to start with, we could start by swapping row 1 and row 2. So we'll say that's our first step. So let's switch row 1 and row 2. And here's what that looks like. We have 1, negative 2, 4, 3, 2, 4, and then the last row doesn't change at all. Okay, so 1 is going to be our first pivot entry, or in other words, the first non-zero value in the first row. And when we convert this matrix to reduced row echelon form, we want each of the values below the 1 to be zeros. So how can we first convert this 3 to be a 0? Well, let's make a little room here and rewrite this matrix. Okay, so we've rewritten the matrix right here, and we want to figure out how can we convert this 3 to be a 0? Well, notice if we do 3 minus 3 times row 1, that would be 3 minus 3, and that would get our 0. So let's say the new row 2 is going to be row 2 minus 3 times row 1. So here's what that would look like. So the first row doesn't change. We'll just go ahead and rewrite those values. And the last row doesn't change, so we'll rewrite those values as well. Now in the second row, we have 3 minus 3 times 1. So 3 minus 3 is 0. And the next value, you have 2 minus 3 times negative 2. So 3 times negative 2 is negative 6. So 2 minus negative 6, that's the same as 2 plus 6. So that's 8. And then this last value, we have 4 minus 3 times 4. So 3 times 4 is 12. So 4 minus 12, that's a negative 8. Okay, next we want to figure out how can we make this negative 1 a 0. Well, notice if we just do negative 1 plus 1, that would get 0. Or in other words, the value in row 3 plus the value in row 1, that would produce a 0. So let's write that over here. Let's say the new row 3 is going to become row 3 plus row 1. So here's what that looks like. We'll rewrite the first two rows since those aren't going to change at all. 0, 8, negative 8. Now row 3, we said that will become negative 1 plus 1, that's 0. The next value is 1 plus negative 2, that's negative 1. And this last value is negative 3 plus 4, that's a positive 1. Okay, so our first pivot entry has all zeros below it, that's good. Our next pivot entry, in other words, the next non-zero value in the next row, we see is an 8 right now. And we want it to be a 1 in reduced row echelon form. So the easiest way to do that would just be to take row 2 divided by 8, because that would be 8 divided by 8, and that would get our 1. So we'll say the new row 2 is going to become row 2 divided by 8. So here's what that looks like. The first row doesn't change at all, and the last row doesn't change at all. So we'll write those. Okay, row 2 is row 2 divided by 8. So 0 divided by 8, that stays a 0. 8 divided by 8 is 1, and negative 8 divided by 8 is a negative 1. Okay, let's rewrite this matrix over here. Okay, so recall that when we have our pivot entries, we want all of the values below the pivot entries to be equal to 0. So we need to figure out how can we make this -1 equal to 0. Well, notice that we could just do -1 plus 1, or in other words, row 3 plus row 2 to convert this to 0. So we'll say the new row 3 is going to become row 3 plus row 2. So here's what that looks like. The first row doesn't change at all. The second row doesn't change at all. And in this last row, we have row 3 plus row 2. So 0 plus 0, that stays a 0. -1 plus 1 is a 0. And 1 plus -1, that's also a 0. All right, so there's one last step to get this to reduced row echelon form. We said our pivot entries have to have all zeros below them, but in reduced row echelon form, they also have to have zeros above them. So this -2 right here, this needs to become a 0. So how could we do that? Well, notice if we just take row 1 and we add 2 times row 2, that would be -2 plus 2 times 1, that would get a 0. So we'll say the new row 1 is going to become the original value in row 1 plus 2 times the value in row 2. So here's what that looks like. We get 1, we'll rewrite the second and third rows since those won't change at all. Okay, we get row 1 plus 2 times row 2. So -2 plus 2 times 1, that's 0. And then we get 4 plus 2 times -1. So 2 times -1 is -2. So we get 4 plus a -2, that's a 2. So this matrix is now in reduced row echelon form. Because the pivot entries are all 1, there are zeros above and below both pivot entries. And actually another requirement is that if there is a row of all zeros, it's at the bottom of the matrix. And that requirement is also met. This row of zeros is at the bottom. So now that the matrix is in reduced row echelon form, we just have to ask ourselves, is there at least one solution to this system of equations that this matrix represents? Or in other words, is there anything that doesn't make this system inconsistent? Well, down here, we see that 0 times something plus 0 times something must be equal to 0. So that's perfectly possible. So the only way that this system we would say is inconsistent or has no solution is if we had, let's say, something like this, a 0, and like a 5 at the bottom, because that would say 0 times something plus 0 times something is equal to 5, which is never possible. So we would say that this system is consistent, which means it has at least one solution. And actually, there is one solution. So if you'll recall, the first column represented the vector u1, the second column represented the vector u2, and this augmented column represented the vector v. And we were really asking ourselves, is there a way to write c1 times u1 plus c2 times u2 is equal to v, where the c1 and the c2 were constants? Well, the nice thing about reduced row echelon form is that it allows us to see what those constants are that we can plug into here to make this a true equation. So we see that the constant for u1 is equal to 2. So we can write 2 times u1. The constant for c2 is equal to -1. So we'd say minus 1 u2 is equal to v. So this is how we could write v as a linear combination of u1 and u2. And if you'll recall, the original values for u1 were 3, 1, -1. The original values for u2 were 2, -2, and 1. And the original values for v were 4, 4, -3. So what we see is this equation does hold true. So if we say 2 times u1 minus 1, we can verify that we actually get these answers. So if we say 2 times 3, that's 6, minus 1 times 2, so 6 minus 2, we get 4. 2 times 1, that's 2, minus 1 times -2, which is a positive 2, so 2 plus 2, that does get us 4. And lastly, 2 times -1, so -2, minus 1, -2 minus 1, that is -3. So that's a way to double check ourselves. So in the end, we're going to write yes. It is possible to write v as a linear combination of u1 and u2. And this is the actual formula that we can use to write that linear combination.